This playlist deals with some aspects of Eurocode 2 version 2023. Watch this playlist for further selected topics. This video is about Clause 8, Ultimate Limit State, and it's the third video in punching shear. We will deal now with the situation where tau RDC is smaller than TED, meaning that there is a need for punching shear reinforcement, and we will now give you the formulas for calculating the punching shear reinforcement. So we are in a situation where the applied or the design shear force is bigger than the shear force resistance of the concrete. Just as a reminder, the applied shear force or the design shear force is equal to this formula. And the resistance of the concrete, the shear resistance of the concrete is equal to this formula, with Kp equals to this. Now, when tau ED is bigger than tau RDC, then we have to apply shear force reinforcement, and the shear stress in the shear force reinforcement, the design value of it, is of course a combination of the resistance of the concrete and the resistance of the shear force. And the proportionality factor is eta C and eta S. Of course, the total resistance must be bigger than rho W F Y O D. Eta C is the ratio of the resistance of the concrete divided by the applied shear stress. Eta S is a function of eta C, is a function of KPB, it's a function of DDG and DV, and a function of the diameter of the stirrups and DV. Calculating directly ASW, just the reinforcement, the needed reinforcements of the stirrups, is getting a little bit complicated. First of all, because we are working in stresses, in shear stresses, and now we have to rework all those different formulas. Rho W, the shear force reinforcement, is equal to ASW divided by the radial spacing divided by the tangential spacing. This formula, formula 807, is valid for vertical shear reinforcement at the investigated control parameter. Up till now, they talked about the control parameter at 0.5 dV. And in the formula 8.107, they talked about the investigated control parameter. So there are more control parameters. For inclined shear reinforcement, of course, you have to multiply it by the sinus and the cosinus of the angle that is made by the inclined reinforcement, which has an angle between 45 and 90 degrees. For single bent-up bars, it's of course multiplied by sinus of alpha W. You see that SR, the radial spacing of the punching reinforcement, is dV divided by the sinus of alpha W. This condition must be valid. So not all the angles are okay for a certain eta S value. ASW is the area of one leg of shear reinforcement. ST is the average tangential spacing of perimeters of shear reinforcement measured at the investigated control perimeter, which is in fact the length of the investigated control perimeter divided by the number of shear reinforcement bars arranged on it or near to it. That's why we call it average. And the radial spacing is the maximum of S0 plus S1 over 2 or S1. Now there's a little drawing explaining this. 1 is the supporting area. S0 is the location where the first leg of the stirrup is situated, and S1 is the width of the stirrup, or the distance between the two legs of the stirrup. Looking at this formula, it does not make much sense to me. The maximum of S1 compared with a distance from the support up till the midpoint of the stirrup. So it's a little bit strange. In outer perimeters of shear reinforcement, without an explicit specification, at least the same amount of reinforcement as in the first perimeter should be provided in each perimeter. It's the first time they talk about outer perimeters. So there are more than one control perimeter. So there is no definition of what is an outer perimeter. It's not stated explicitly. And then there is an outer perimeter without an explicit verification. Means that in this case, you calculate the needed reinforcement for the control parameter B 0.5 dV, B 0.5. You calculate the needed reinforcement, and you use this reinforcement for all reinforcement parameters until you reach out a zone where you do not need reinforcement anymore. There is a distance between each reinforcement parameter, which must be smaller than 0.5 dV or 0.75 dV. You will see that in the next video. There can be an alternative, and it is that the required area of shear reinforcement at the outer perimeters may be calculated according to what we have seen just in the slides before. So this means that you have one control parameter B 0.5, you calculate the reinforcement, then you take the next parameter, which is at 1.5 dV further on, so it's at 1 dV. For this new parameter, you recalculate the needed reinforcement, and so you go on until you reach a parameter where you do not need any reinforcement anymore. You cannot just do it in the same way that you have calculated the needed reinforcement in the first parameter. For the applied or for the design shear force, you must use dV out instead of dV and B05S instead of B05. S means, I'm not 100% sure, but it's most likely, is for instance, the first control parameter after B0.5 is in fact the control parameter B1.0. So it's at 1 dV distance. So the S is different reinforcement parameters. dV out is a new concept, and dV out, you will just see it right now. For KPB, in the different formulas to calculate the needed reinforcement of the perimeter outside B 0.5 means that B 0.5 S. So let's call it the perimeter S, the reinforcement perimeter S, or the reinforcement line S. You use B05S instead of B05. And B0S you use instead of B0. So it means that B0S is different from B0, which is confusing because B0 is the perimeter at the edge of the support. So what is B0S then? B0S is at the distance dV over 2 or dV out over 2 from B05S. And KPB, you have to multiply the previous formula of KPB with the square root of dV divided by dV out. dV out was a new concept, and dV out is in fact the outer shear resistance effective depth, and it's accounting for the possibility of delamination in compression surfaces. So that's why outside the first control perimeter, you need to have another effective depth, dV out. And dV out is defined as dx plus dy divided by 2 minus CV. Formula 8.91 gives a definition of dV, and it's equal to dV in the direction of x and dV in the direction of y divided by 2, the mean of it. But in Formula 8.108, they talk about dx and dy. This is not defined. So I suppose that this should be reading as dvx and plus dvy. So assuming this, then you will see that dv out is equal to dv minus s minus cv. Cv is defined by figure 8.23 and not by a formula. So you see here, there is some distance cv. I do not know directly how to calculate this. It's most likely to do with the radius of the band, the point of gravity or of the stirrup, and the concrete cover. So you can find something for this. In this case, when there is a rebar, which is almost always the case, and there's a rebar in the longitudinal direction, then you get here to 0.4. But what's 0.4? Is it the point of gravity of the longitudinal reinforcement, or is it at the end of the bend? This looks further away than this one, so it's not very clear. I suppose that this is the point of gravity of the longitudinal reinforcement. For studs, it's clear what CV is, but now you have to decide in your design problem what is CV. You do not know yet what reinforcement you need as shear reinforcement, but you have to estimate directly CV. And with inclined stirrups or inclined shear reinforcement, it's even more unclear how much CV is. I've made now first something else. The radius, of course, of the bend in the stirrup, it has to do with the mandrel diameter, and you see that it depends, of course, on the size of the stirrup. It's 4 times the size of syrup, or 7 times the size of the syrup. So CV can be a large number, a relative large number, if you have diameter 16 or more. I've made for vertical syrups with not big diameters of stirrups, normal cases. I've calculated with different concrete covers, and I found that more or less dV out can be equal to 0.9 dV. So I recommend, because otherwise it will be very difficult to calculate the needed reinforcement. I recommend just to estimate in the beginning your needed reinforcement you use as dV out 0.9 dV in normal cases. Afterwards, when you have defined reinforcement, you can check it more properly. At last, we have to check if the applied shear stress is smaller than the maximum allowable shear stress due to the compression in the concrete. It means that tau ED must be smaller than tau RD max. Remember, tau ED was equal to this formula, and tau RD max is equal to, or is proportional to, tau RDC, and the factor is N cis. Tau RDC, just for your reminder, is equal to this formula, and N cis is for studs, this formula, and for links and stirrups, the other formula. At the shear stress, the applied or the design shear stress equals to the maximum allowable shear stress, then this happens, of course, when the applied shear force is equal to the maximum allowable shear force for the compression of the concrete. In practice, we calculate with the shear force, not with the shear stress, because all your programs give you shear force and not necessarily shear stress. So now we have to rework the different formulas, and GRD max is then equal to N cis tau RDC B 0.5 dV over beta E, which is a simple formula. But pay attention. VRD max is now defined relative to B 0.5. According to the Eurocode 2 version 2004, VRD max was defined relative to mu0, which is in fact B0, which is the perimeter just at the face of the support. So this is a big difference between those two. Don't make a mistake of that. On the x-axis, we have the concrete quality. On the y-axis, we will have the ratio of VRV max with as a reference value the value for the Eurocode 2004. And then you will see that when the concrete quality increases, that the maximum allowable shear force is decreasing in respect to the code 2004. You will notice that every value is below 1. So VRD max is now much lower than the VRD max as it is today. And you will see that, for instance, for a concrete grade 30, you will have 25% more or less capacity in VRD max. Of course, when you have on the x-axis the concrete quality and the y-axis just VRD max in kilonewton, and then you see that the red line is the reference line 2004, the blue one is for 2023, and you will see immediately that the present value is much lower than or that the value for the code 2023 is much lower than the present value. You will also notice here a small change in direction of the curve, and this is due to the fact that DDG is due to the definition of DDG, which is changing after FCK is bigger than 70 megapascal. Further control parameter B05 out shall be checked according to the previous formulas that we have seen. So first we check one parameter B05. We calculate the needed reinforcement, and we put this reinforcement, for instance, in each reinforcement parameter that is needed. And at the end, we will check B05 out, and the outer control parameter at which shear reinforcement is not required is equal to this formula. So this is now B05, not S, but B05 out is B05 times this factor. In Eurocode 2 version 2004, mu out, which is more or less the same as B05 out, mu out was defined where the shear for where the applied shear force is equal to the shear force that can be taken up by the concrete, or where tau ED was equal to tau RDC. But this is strange, because if this is the definition of mu out, or if this is the definition of beta 0.5 out, if the definition is the same, well, one could expect that, because it says the outer control at which shear reinforcement is not required, which is this condition. Then something strange happens, because B05 out will then be where tau ED is equals to tau RDC. That means if this is equal, that eta C is 1, because that's the proportionality between those two. And if eta C is 1, then why is there an eta C in this formula? So if this is a definition of beta 05 out, then the eta C is there for nothing. So that's why I'm convinced that the definition of beta 05 out is not the same as in Eurocode 2 2004. dV out, we have seen, is dV minus CV. Eta C was this proportionality. And we can have a little check on this formula just to prove this, or prove this in fact. It's obvious that the applied shear stress is bigger or equal to the shear stress in the concrete, in this case here, for calculating at the outer control parameter. That means that eta C is smaller than 1. Eta C cannot be bigger than 1, otherwise this is not right. Eta C, because eta C is always smaller than 1, that's okay. Then dV over dV out, we have seen that dV out is 0.9 dV, so this is always bigger than 1. That means that if this is smaller than 1, this is bigger than 1 square of it, then B05 out is bigger than B05, which is logic. Eta C can never be bigger than 1. Otherwise, you will have a problem, and then B05 out can be smaller than B05, which is not logic. So that's why I believe that the definition of B05 out is different than the one in Eurocode 2 2004. And of course, tau ED equals this formula just complete.